So in this lecture we talk about types. I've said before that Julia is a strongly typed language. It's a language with an intricate type system, and if you want to, you can make use of this type system in great detail. However, the good news for a beginner is that you can simply ignore type. Julia will take care of type for you. The only reason for you to know about types at all as a beginner is that, unfortunately, if you make a mistake, Julia will throw an exception, will throw a bug, and you may have to go back and find out what the mistake is. And often the information Julia gives you is that there's some sort of problem with a type you used.
Here we get into something that is very special to Julia. Before we start, let me reassure you, you can almost always ignore the types when you write Julia code. You can completely ignore it and just go on. What might happen, however, is that your code runs slowly. In that case, you will want to tweak it, which usually means that you will be working on getting the types right. The one reason that you cannot ignore types is that error messages occur, and they tell you about the type, and they might complain about the types. For purposes of debugging, it is essential to know about Julia's type system, and that is why we included this early in the course, even though when you write your own code, you can actually almost always ignore it. Alright, so what are types? Types are formats for storing information. Suppose we have a sequence of zeros and ones. We all know that that's how computer code actually represents information. 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, all these zeros. It becomes completely meaningless to a human being, but it's perfectly meaningful to a computer, isn't it? No. The computer does not know whether this represents a color or whether this represents the start of a mathematical formula or whether it represents a whole bunch of different numbers. Unless the computer is told what format of information is being conveyed by this sequence of zeros and ones, it doesn't know. Every computer language has its own way of specifying the formats of information it can use, and those are its types. Julia also has a type system, and it is quite elaborate. So if you store the information, you have to also store the type. But where is it? Is it part of the variable, or is it in a different place, or how? In the case of Julia, only values have types. If we look at 1, 3, 5, we enter that, the output is 9. 1 has a type, 3 has a type, 5 has a type, and 9 has a type. You need a lot of careful management inside the computer to make sure that the type information of 1, the type information of 3, the type information of 5 are combined and stay together and give you the type information for 9. In Julia, of course, we don't have to worry about that. Those details are taken care of. It's easy to determine type in Julia. There's a built-in function type of, and if we apply it to the number 1, we see that number 1 has the int 64 type. If we add 1 to 3 to 5, they're all of type int 64, and so is the result. If we want to determine the type of the very first string we entered, hello world, it's called an ASCII string. Here's a different kind of string. It uses Greek letters. Greek letters are easy in Julia. They're part of Unicode, and we enter them as Unicode, which we'll see in a minute how to do. The result is now what is called an UTF-8 string, not an ASCII string. If we have H by itself, a single character, but in double quotes, that's still an ASCII string, but in single quotes, it is the type char. Here we have 1 plus 3 plus 5 again, but now the result is a float 64, not an int. Julia is very sensitive. The only difference between this and that is this full stop after the 5. But you need not worry about the types if you don't want to. Julia will automatically take care of types. On the other hand, you could specify in great detail what you want to have done about types. You can even extend Julia's type system with your own user-defined types, and this can really help speed up code, although that's not part of our course. Right, let's look at the characters and the strings. and the types that can arise. A string is just a sequence of characters. If we're using Roman letters, all the necessary characters are on your keyboard, and they are the original ASCII characters. There are 128 of them, so the 52 upper and lowercase Roman letters, and then 10 numbers, and that's 62, and a whole bunch of other punctuation signs and so on, but in the end only 128. Those are the original ASCII characters. They are the ones that go into ASCII strings. Unicode, we want to enter more. So for instance, this alpha here was entered as follows. I start with a backslash. I then type alpha and I press the tab. If I start and I write only alpha and I press tab, it gives me the option of going to alpha. I say yes, I press tab again, and that gives me alpha. This is plus minus. If you know LaTeX, you will know that plus minus is just PM, and you enter. Suppose you want to see diamonds. So you want to see, and you think that diamonds is how you enter it. If you press tab, the option is diamond suit. If press tab again, we do. Okay, so let's say club suit. And there it is. If you know Unicode, many Unicode characters are specified in terms of a backslash followed by letters from the Roman alphabet. They can be done like that. Others have numerical codes, which you can also use. But all of them have essentially the same kind of type, which is the type char, which we saw before. So as we saw in Julia, the type character starts with a capital letter. All the types start with capital letters. The ASCII strings type is made up only of ASCII characters, and the UTF-8 string is made up out of Unicode characters. True and false are values of a particular type, namely bool. It comes from George Boole. He suggested that all logic could be presented in terms of the value true, false, and he developed an algebra for doing logical calculations. So this is an extremely simple type. It has only 2 values. It occupies only 8 bits. Rather more complicated are the types int64 and float64. To do technical and scientific computation efficiently, we must handle numbers efficiently. Julia has a great many number types. The most important are these two, int64 and float64. They both use 64 bits to represent the number, but they represent these bits quite differently, even if the values are the same. So the formats are quite different, and they are dealt with at the computer level in different ways. We don't have to worry about that in Julia. Julia will take care of that for us. But we do have to worry about the difference in how they are typed. When we use a decimal point, that is a floating point number in Julia, and when we don't, that is an integer. Let me emphasize that. That explains why 1 plus 3 plus 5 point ended up as the type float64, not int64. So if we compare numbers of different types, it's still true or false that 2.0 is equal to 2. So in Julia, that comes out as true, even though the types are different. And again here, the type of 3/2 is float64, the type of 2 is 2, but it is of course false that 2 is less than 3/2. If we were interested in the really strict comparison, we want a 2.0 compared to 2 not to be true. We would use the operator equals equals equals, which is the strict comparison operator. That's true only if the values and the type is equal. So 2.0 is strictly speaking not exactly the same as 2. Now, it's important in Julia to distinguish between concrete and abstract types. So the types we've seen so far are concrete types, which simply means that they do not have subtypes. int64 and float64 are of course both numbers, and so in some sense we would like to be able to group them together. For instance, one would like to do things with numbers without knowing exactly what type of number you're dealing with. Every type in Julia, except the type any, has a supertype. For float64, the supertype is real. However, for int64, the supertype is signed. Then signed is underneath the supertype integer, and integer sits below real. So both int64 and float64 sit below the type real, but int sits in some sense lower down below real than float64 does. So real, integer, signed, these are all abstract types because they have subtypes. As we said, when you have a value in Julia, the type must be a concrete type. So what are abstract types for? The idea of an abstract type is to guide type conversions. For instance, some operations change the type of a value. Abstract types guide this process. On the other hand, abstract types help you to write functions. We'll see in lectures 8 and 9 exactly how this works. Basically, if we write a function that works on an abstract type, it works for all the types that sit underneath that abstract type. As was noted above, you don't need to worry about type specifications at all. You can simply ignore them and Julia will take care of it. Julia will use abstract types for you in your code. In fact, your functions, for instance, will all assume that the type of the variable is any. Julia has a tree of types, which simply means that as you go up from your concrete types up to any, there is exactly one route for every concrete type up to any. You don't have alternatives that you can take. And this makes it completely unambiguous exactly how types relate to each other, which is why Julia can efficiently deal with types.